Hey there, and welcome to your personalized deep dive.
Mhm.
Today, we're tackling the fascinating world of machine learning.
Mhm.
Specifically, we're taking a deep dive into the transformer,
Okay.
a model that's been making waves in AI. You've sent over some excerpts from the original Attention is All You Need paper,
Right.
and we're going to break down why it's such a big deal.
This paper was a game changer when it came out back in 2017, and its impact is still being felt today. It's like the foundation for so much of what we see in AI, from language translation to those eerily accurate text predictions on your phone.
Okay, so let's set the stage. This paper focuses on how computers understand and process sequences,
Yeah.
like sentences, where word order is crucial, before the transformer. Recurrent neural networks, or RNNs, were the go-to solution.
Yeah.
But like anything in the fast-paced world of tech, they have their limitations.
Right. Imagine reading a sentence word by word and trying to hold the entire meaning in your head until the very end. RNNs faced a similar challenge. That sequential processing made it hard for them to handle those long-range dependencies in language, especially in complex sentences.
The paper uses the example. It is in this spirit that a majority of American governments have passed new laws since 2009, making the registration or voting process more difficult.
That's quite a mouthful. Trying to remember what it refers to at the beginning while you're all the way at the end sounds like a recipe for confusion.
Absolutely. A traditional RNN could get bogged down trying to make that connection over such a long stretch of text. And that's one of the key problems the transformer aimed to solve. Instead of processing information bit by bit, the authors proposed a radical idea.
Attention.
Attention. So like teaching computers to focus like humans do.
In essence, yes. The transformer was revolutionary because it moved away from that step-by-step approach of RNNs. Instead, it allowed the model to attend to different parts of the input simultaneously. Imagine being able to instantly reference any part of a document, no matter how long, to understand the context.
Okay, that's starting to click. So instead of reading a sentence like a line of dominoes, the transformer can jump back and forth connecting the dots between words no matter how far apart they are.
Exactly. It's like having a mental map of the entire sentence where you can instantly zoom in on any detail you need. This attention mechanism allows the transformer to capture those long-range dependencies that tripped up RNNs.
Fascinating. But how do they actually implement this attention thing? It sounds almost magical.
Well, it involves a bit of math, but at its core, the idea is surprisingly intuitive. Imagine you have a giant key ring with hundreds of keys, and you need to find the one that opens a specific door.
Okay, I'm picturing it. Go on.
Each key on your ring is like a key in the transformer's attention mechanism, and behind each door is a value. The query is like your intention you're asking, which key opens this particular door?
So in our sentence example, the query is like our current focus, and the keys and values are all the other words we could potentially connect it to.
Precisely. The attention mechanism calculates a compatibility score between the query and each key. Think of it like the mechanism is checking how well each key fits into the lock. The higher the score, the more attention the query pays to the value behind that door.
So the model is essentially ranking how important each word is in relation to our current focus, and then using that ranking to understand the overall meaning.
Exactly. It's like shining a spotlight on the most relevant parts of the input, allowing the model to focus on what matters most. And here's the really ingenious part. They didn't just use attention in one place. And here's the really ingenious part. They built an entire architecture around it.
Okay, let's unpack this architecture a bit. What do they actually build?
They created a system where instead of just having one attention mechanism, you have multiple heads of attention working in parallel. Think of it like having a team of experts, each with a slightly different focus, all looking at the sentence at the same time.
So instead of one spotlight, we now have multiple spotlights, each highlighting different aspects of the sentence.
You got it. Each attention head can focus on different types of relationships within the input, like how words relate to each other grammatically, or even the overall sentiment of the sentence.
And this multi-head attention was just one part of their innovation, right? Didn't they also find a way to deal with the speed limitations of RNNs?
They did, and that's where it gets even more interesting.
So how did they tackle that speed issue? It sounds like we're about to get into some serious AI engineering.
Well, remember how we talked about RNNs struggling to process long sentences because they handle words one by one? The transformer tackled this head-on with a clever technique called positional encoding.
Positional encoding. So giving the model a sense of word order without making it read the sentence in chronological order.
Precisely. Imagine giving each word a little tag that tells the model where it stands in the sentence. It's like numbering the words, but instead of just 1, 2, 3, these tags are more complex, encoding positional information in a way the model can understand.
Okay, so it's like giving the model a cheat sheet about word order so it can focus on understanding the relationships between those words more quickly.
You got it. And the results were impressive. In the paper, they describe how they trained a model to translate English to German using this new architecture. This model achieved state-of-the-art results, even surpassing models that combined several different approaches.
That's a bold claim. But what about the speed improvements? How much faster are we talking?
Fasten your seatbelts. It only took them 3.5 days to achieve those incredible results.
3.5 days, that's lightning fast in the world of machine learning, especially for such a complex task.
Absolutely. The attention mechanism played a crucial role, but it was the combination of these innovations, including positional encoding, that led to this remarkable speed boost.
It's amazing how these seemingly small tweaks can have such a dramatic impact on performance. But before we get too lost in the technical details, let's zoom out to the bigger picture. This paper wasn't just a breakthrough in machine translation, was it?
You're right. The authors had much broader ambitions. They saw the transformer as a versatile tool with the potential to revolutionize how we process any kind of sequential data, not just language.
So not just text, but also things like music time series data, maybe even DNA sequences.
Exactly. They even hinted at applying it to images, audio, and video down the road. In fact, they specifically demonstrated the transformer's flexibility by applying it to a task called English constituency parsing.
Constituency parsing, that's a new one for me. Could you refresh my memory on what that's all about?
It's essentially about unraveling the grammatical structure of a sentence, figuring out how words group together to form phrases and clauses. Think of it like those sentence diagrams we used to do in school, but instead of drawing them by hand, the model learns to do it automatically.
Ah, right. Those diagrams with all the branching lines and parts of speech. Not my favorite grammar lesson, I have to admit.
Well, it turns out the transformer is a natural at it. Even though the structure of this task is quite different from translation, the model still achieved impressive results, even surpassing some models specifically designed for parsing.
Wow, it's like they invented a Swiss Army knife for language processing. One model that can tackle all these different challenges, and to think this was all laid out in a single paper.
It's a testament to the power of this architecture and the vision of the researchers who developed it. And the best part is they knew they were onto something big. They didn't just present their findings, they also highlighted the limitations of their approach and pointed the way forward for future research.
Well, that's interesting. So they weren't shy about acknowledging that their work was just the beginning.
Not at all. In fact, they openly discussed the challenges of scaling up this technology to handle even larger data sets and more complex tasks. They recognized that the computational demands were significant, even with the efficiency gains they had achieved. It was almost like they were throwing down a gauntlet for the next generation of researchers to pick up.
A challenge to push the boundaries even further. And from what I understand, the research community definitely rose to the occasion. It's incredible to think that this one paper, with its insights about attention and efficient architectures, sparked such a wave of innovation in AI. It really goes to show the power of a truly groundbreaking idea.
Absolutely. The transformer didn't just solve a technical problem, it opened up a whole new way of thinking about how machines can process information. And the authors, in highlighting the limitations of their work, essentially handed the research community a roadmap for the future.
And one of the big challenges they pointed to was the issue of scale. Even with its efficiency gains, the transformer still required immense computing power, which isn't exactly something everyone has lying around.
Exactly. It's like they were saying, okay, we've built this amazing race car, but it needs a massive track and a whole pit crew to run properly. How do we make it accessible to more people?
So make it less reliant on those massive data sets and huge computing clusters. Democratize AI in a way.
Precisely. One of the big open questions they posed was, can we achieve similar results with smaller models trained on more readily available data? Because right now, there's a real risk that the most powerful AI tools will only be accessible to a select few.
And that's not just a technical problem, it's a societal one. Because if we want AI to benefit everyone, we need to make sure the tools are available to everyone, not just those with the biggest budgets.
Exactly. And that's why I think the next big breakthrough in AI won't just be about making models bigger and faster. It'll be about making them smarter, more efficient, and more accessible.
So more brains, less brawn.
Exactly. Imagine a world where instead of needing a supercomputer to train a cutting-edge AI, you could do it on a laptop. Think of the possibilities.
It's like the difference between having a giant printing press and being able to print a book from your own home. Suddenly, the power to create and innovate is in everyone's hands.
Precisely. And that, to me, is the most exciting legacy of the Transformer paper. It wasn't just a technical achievement, it was a call to action, a call to make AI more powerful. Yes, but also more equitable and accessible to all.
And as we've seen, when the research community rallies around a big idea, incredible things can happen. So to bring it back to you listening, think about this. What are the transformers waiting to be discovered in your field? What seemingly impossible problems could be solved if we could find a way to make these powerful AI tools available to everyone?
Because even though this paper focused on language, the implications extend far beyond. It's about unlocking the power of information, finding patterns, and making connections that were previously hidden in plain sight.
It's about asking the big questions and pushing the boundaries of what's possible. So as you go back to your own work, your own research, your own creative pursuits, keep those questions in mind. What are the hidden connections in your data? What could you achieve if you have the right tools, the right insights at your fingertips? It's something to chew on. Until next time, happy exploring.